Okay, as we said, in the modern times, now we know a lot about El Nino, its dynamics. Forecasting has gotten so much better, especially because the teleconnections are very important. And the biggest of the teleconnections, of course, involves impacts on rainfall during the summer, precipitation of all sorts in the winter, and impacts on agriculture essentially across the globe. This makes it necessary that we also worry about El Ninos during the Holocene, and obviously they were a part of natural variability throughout the Holocene. There is a lot of work done on El Ninos during the Holocene, and we have to say up front that the consensus on exactly how El Nino varied through the Holocene in terms of its duration, frequency, and intensity are not always agreed upon. So this is one rendition here from NOAA, but you can see this is a rather old paper here. I took the figure from the same book that we used before, Climate Change and Cultural Dynamics. So it talks about summary of the number of moderate, strong El Nino events in 100-year windows since 12,000 calendar year BP, based on the analysis of classic laminae in Lake Laguana, Palcacocha, southern Ecuador. The solid line indicates minimum number of events, 5 required to produce ENSO band variance. Data available from NOAA NGDC Paleoclimatology website. There are many issues in reconstructing El Nino in the past as well. The data is not resolved at the time scales you would want. El Nino is an interannual event, so something like monthly data would be fantastic, but that's not what you always get. That's why you use thresholds like this to pass through the ENSO band variance, and then you're looking for the change in that 5-year ENSO band variance per 100 year, and this would argue that there is variability throughout the period, and maybe there is increased variance here in more recent times. And many papers have argued that since about 6,000 years there is an increased variance per 100 year. How does it translate actually to agriculture on year-to-year basis, or in chunks of decades, which would affect agriculture seriously enough for societies to do something about them, plan for them? If, for example, a La Nina pattern persisted in the Eastern Pacific, that would produce persistent cold, dry condition or drier conditions, or western eastern part of the Pacific, so western coast of North and South America. So the civilizations that were in the Andes would have paid a price, right? So atmosphere-ocean feedbacks during El Nino southern oscillation can be understood briefly. I have many podcasts on this, so I won't go into details, but there is a mean structure which shows trade winds from the southwest and northeast, which converge into the ITCZ. Wherever you have minimum wind speed, you end up with warm sea surface temperatures because the latent heat loss is reduced and there is ocean dynamics involved, like the mixed layer thermocline interactions, which can produce warm SSTs. Those winds push the water westward and pile them up and warm them along the way. But when you try to push the water eastward, Coriolis pushes the water away from the equator on both sides, so you are parting the water like Moses. So cold waters come up, and they are also nutrient rich and CO2 rich, so there is CO2 coming out of the ocean here when there is upwelling or cold water coming up, and nutrients produce phytoplankton, which means there is a rich supply of fish and seabirds as well. And Galapagos, of course, is known for its biodiversity, and many of the epiphanies that Charles Darwin had occurred when he was on the Galapagos for several months when Beagle was parked there. Okay, so wherever there is warm water in the ocean, atmosphere tends to pick up moisture through evaporation. As air rises, it expands, cools, and condenses, so you get rising motion and convection, and about 5 meters of rain falls here on average per year. The air that rises hits the ceiling, the tropopause, which again I've explained in other podcasts, and it diverges and it sinks over the eastern part. Sinking air produces subsidence produces high pressure, clear skies, no rain, which is consistent also with the cold temperatures. And there are other parts of the so-called Walker cell. Sir Gilbert Walker was the first one to notice a pressure oscillation between Darwin here and Tahiti here in the central eastern Pacific, and he knew that the southern oscillation or the pressure oscillations between Darwin and Tahiti were closely related to droughts in the monsoon, which was his main interest. So in his honor it's named the Walker cell, and Walker cell gets perturbed during an El Nino and La Nina, as we will see in a minute. And there are feedbacks here which are called Bjerknes, which is called Bjerknes feedback, which basically means when you upwell cold water, you increase the sea surface temperature gradient from cold to warm, which is associated with the pressure gradient, which produces winds, which can feed back to make the upwelling stronger. As it is colder, pressure gradient stronger, winds stronger, and so on. So during an El Nino, the warming that happens here weakens the sea surface temperature gradient, weakens the pressure gradient, weakens the winds, further feeds back to weakening the upwelling and warming, and so on. So of course you need something to turn off this feedback, and there are waves involved which do the work in terms of turning off the growing feedback. There are many theories which we will not get into, because when you are in this normal condition or in the La Nina condition, water that's getting pushed here and getting heated is accumulating. So there is a theory of recharge discharge, which says waters warm up and accumulate for some time, and they are discharged, and then they start to accumulate again. So if the waters that are accumulated are discharged, then the El Nino ends. So that can be a negative feedback as well. Okay, so this is a La Nina, atmospheric ocean feedbacks during El Nino southern oscillation, referred to as ENSO. Of course, I think everybody knows why it's called a La Nina. Basically, the warmer than normal waters arrive around December, January, February. The Spaniards who colonized these regions noticed the near Christmas time warm waters, and they thought this was a gift from God. So they called it the God's child, Christ's child, as in El Nino, the little child, little boy. And we cannot call the opposite phase as anti-El Nino, because that could be anti-Christ. So we call it the La Nina. So you can see now winds are stronger, colder than normal anomalies. The thermocline that is pulled up by the upwelling is even closer to the surface here compared to neutral years. The warm waters that accumulate here push the thermocline down, so warm waters above the deeper thermocline. So the thermocline gets shallower here and deeper there, so waters are warmer than normal here in general and squished more because of the stronger winds. You get more rain over here, so you would have floods over Australia, Indonesia, and maybe even the Indian monsoon gets affected on many occasions. East Africa, Brazil, US, pretty much the entire planet gets affected, as we will see in a minute. Okay, so stronger upwelling also means colder temperatures, and again you can go through the Bjerknes feedback with stronger pressure gradient, stronger winds, stronger upwelling, and so on. During a El Nino, the waters slosh eastward, either because the trade winds get stronger or because there are anomalies, westerly anomalies here that push the waters eastward. When the waters move eastward, the convection moves with it. The thermocline is deeper because the upwelling is weakened, and the warm waters are now spread throughout the tropics to the east, as you can see, and there are changes in the warm waters here as well that we see under the ITCZ here and here. So the entire Walker cell is perturbed. during an El Nino as well. And the main point is that the west coasts of the Americas become warm, wet, and winter precipitation can be high. Mudslides, floods, etc. occur here, but upwelling also kills fish and seabirds and so on. And of course on this side you get droughts, dust storms, and again the teleconnections or the impact of El Nino are global. So those have to be looked at in the Holocene time period. This is a paper from Zhengyu Liu, which used a transient climate simulation. So it made a simulation for the whole Holocene period starting from the last glacial maximum, used the insolation forcing, orbital forcing, and looks at the El Nino strength, which is defined as a index of anomalies in the central eastern region. When these anomalies here, sea surface temperature anomalies or deviations from normal, are warm, you call it El Nino. When it's negative, you call it La Nina. So you look at how that index has changed over time. So you can see Nino 3.4 strength measured here, and the annual cycle of Nino 3 for the two periods are shown as well. So ENSO, the Bjerknes index, and the annual cycle. Bjerknes index is basically an index of how waters are getting advected from west to east and east to west, which is an indication of how strong the ocean dynamics and atmospheric dynamics are together to produce the El Ninos and La Ninas. This is the austral winter JJ insolation at 30 south. The amplitude of ENSO here, B annual cycle of Nino 3.4, and the Bjerknes index in the eastern Pacific. So that is dateline to 80° west and 5 south, 5 north. All are calculated in a 300-year windows, with black for the trace and cyan for orb. So those are different simulations. In BNC, the gray bars at 6 and 21 kiloyears represent the median and 75th and 25th percentile deciles, shown here at the beginning. Okay, 75th and 25th centile, sorry, of the amplitudes of ENSO, and annual cycle in the mid-Holocene and LGM. So the annual cycle shown here is for the mid-Holocene and the last glacial maximum. You can see the flatter temperature gradient and stronger temperature gradient and so on, based on which part of the Holocene you are in, or going back to the last glacial maximum. And they are also using experiments from the so-called Paleo Model Intercomparison Project 2 and 3. The point is, again, that if you look at the El Nino strength as an index in Nino 3.4, you can still see the kind of ramping up of the El Nino strength over here, maybe from about 6,000 years onwards in the different reconstructions. So translating that to what happened to the settlements across the globe, agriculture and so on, is something that is discussed in many studies, and we will see some of those as we go along. But to close this discussion, I would say in the current climate, how El Nino and rainfall are affected or related. So El Nino conditions in the tropical Pacific are known to shift rainfall patterns in many different parts of the world, although they are somewhat they vary somewhat from one El Nino to the next. The strongest shifts remain fairly consistent in the regions and seasons shown in the map, on the map below. So El Nino is not always the same strength in terms of the sea surface temperature anomaly in the Nino 3.4 region. So we have to just do composites to learn the best we can. So these colors correspond to wet and dry teleconnections. Since El Nino happens here and things are changing in distance, we call them teleconnections, and so teleconnections. So July to September here dry, October to January wet here, November to March dry, January to April wet, monsoon, Indian monsoon, June to September tends to get dry, but January to April there is a different signal here of wetness, and October to December wetness as well. And this large band here is a very canonical pattern. June to following January is dry, and July to following March is dry here as well. July to November, July to January. So all these regions are in this band, but the teleconnected rainfall signals and temperature signals are slightly shifted in seasons. Okay, so even North America has signals, November to March, December to March here, Jan to April, November to April. This place gets hit pretty hard, June to following March, April to June, and July to December. And this entire region, June to following April is wet, January to May is wet, and there are some wet signatures here as well during parts of the year. So Amazonia and this region, which had human settlements, there were settlements and agriculture here. There were of course settlements and agriculture here through the Holocene, and in these regions, and of course in Africa and so on, must have been affected by El Nino. Just to close out, La Nina and rainfall, again, it's not perfectly anti-symmetric compared to El Nino. Dry region doesn't necessarily become wet. A El Nino dry region is not necessarily wet during a La Nina because of some dynamic details. There are asymmetries. So you can see that here, for example, this is July to September wet, but this region has different signals than these regions here. Okay, so that has to be kept in mind. And it turns out there are other details, that the East Pacific can remain in a cold state or a La Nina state for multiple years, more than 1 year for sure, and La Nina amplitude can be weaker than an El Nino amplitude. So those kind of asymmetries also matter, especially for regions which are chronically dry when East Pacific is dry. So if a cold pattern persists here, then a dry pattern will persist here, which is what's happening in the last few decades. For example, Western US has become dry and hot because this East Pacific has remained in a La Nina-like state in response to global warming, which is a whole other discussion that you can follow up on my course in tropical dynamics or introduction to climate and so on. And there are wet regions here, again, different parts of the year: November to April, June to December, September to January, May to February, August to December, September to March, and so on. And India tends to be wet, but only about 50% of the El Niños produce a dry signal, and only about 50% of the El Niños produce wet signal. Other dry and wet years are now found to be associated with signals coming from the North Atlantic or the Arctic and so on. Okay, so keeping that in mind, do I want to jump here? Maybe I'll just use this one as well. Global average precipitation anomaly at 12,000 years ago relative to AD 1800. So remember the UV ECSCM output we had seen? It's the same thing. 8,000 years ago relative to AD 1800, 6,000 years ago relative to 1800, and 2,500 years ago relative to 1800. Average precipitation anomalies derived from the long simulation that we had looked at in great detail in chapter 6, I think. Okay, so you can see that this again is precipitation in an unusual event, kilograms per meter squared per second. So 12,000 years ago relative to 1800, there was much more precipitation here, including snow in water equivalent, whereas there were regions which were relatively dry. So coming out of the these are dry regions, negative here, and these are wet regions. Be sure I didn't screw it up. Okay, so Coming out of the last glacial maximum before the Younger Dryas, the polar regions were still fairly cold and dry. Especially the Sahara region into India, and this band across here and this band across here, which potentially correspond to subtropical jets if you know the dynamics, and tropics were generally drier compared to 1800. By 8,000 years ago, this very dry pattern had disappeared. This was still wetter, but this region became wetter or less wet here than 12,000 years ago, but you can see some dry bands here which are milder than before but still extending, and Australian wetness and South American wetness have also receded. 6,000 years ago, more changes. This is getting now wetter, and these regions, this has become significantly drier compared to here, for example. So you can remember that this is where the increased variance of El Nino per 100 years starts, so you can begin to imagine that has to be related to these tropical patterns as well. And by 2500 years ago, you had quite a bit more dryness or reduced precipitation in the monsoon regions. The South Asian and East Asian monsoon regions continued to be dry from this period to this period, and the greening of Sahara has all but gone here. So you can see there's still quite a bit of excess precipitation compared to 1800, but that's all but disappeared here. But the East African region has become more wet in this model simulation. Okay, as you remember, this model is validated against other evidences, so we can trust that this is reliable simulation. So we have to keep these large-scale precipitation changes and the impacts they would have had on agriculture. So we'll come back and look at some specific examples of these in regional scales, so that we can better understand the interaction between climate drivers, human societies, and agriculture, even though we are not always explicitly saying what the agricultural impacts were in terms of crop yields or crop different crops choices and so on. Okay.